Right, so welcome to topic 2 in Newtonian cosmology. And what we're going to do in this topic is really set up the equations which we believe will govern cosmic evolution. And what we did last time was we looked at a set of observations which set the fundamental principles of the universe. So we saw that the universe is finite in age, it has a beginning. We saw that it is currently expanding, and we made the simplifying assumption that it is isotropic and homogeneous. And those three statements are therefore the groundwork to the theoretical backbone that we will develop today. And before we do that, and we're going to do that work in an entirely Newtonian way, but we do need to introduce a little bit of relativity and some concepts of relativity just to understand what some of the things we're going to look at are actually going to mean. And so the first thing we need to think about is how the expansion works and how relativity means that this expansion is slightly different than you might expect, or in fact you might intuit from the Doppler effect. So imagine we're sitting here on the Earth, and around us we have a horizon. And that horizon is simply a distance, and we'll worry more about proper measures of distance later, but a distance c times the age of the universe away from us. So in other words, we can't see beyond this horizon, because in order to do so, the light would have had to travel faster than the speed of light. This is basically as far as we can see in the age of the universe. And we also know that just inside this horizon, in lots of different directions in fact, we can see galaxies. And each of those galaxies have their own horizon. And clearly we can see them. And so their horizon encompasses the Earth. But you can also say, well, what is the velocity that is between these two galaxies here? If you think about redshift, and what redshift's doing is you get to the edge of the universe here, the horizon, the recession velocity, the expansion of velocity, is also taking the universe away from you at the speed of light. And so a common problem people have is, well, what's the velocity if we call this galaxy 1 and this galaxy 2? And then people start getting a bit confused because they start thinking about how you add velocities relative to each other in special relativity and so forth. But here's the difference. Here, this is not a straight Doppler shift of two galaxies that have started in the same place and are moving away from each other in a fixed, pre-existing space. This moving away from each other is caused by the expansion of the universe. So the space-time itself expands. And that means that whilst galaxy 1 is receding from us at less than the speed of light, and galaxy 2 is receding from us at less than the speed of light, galaxy 1 recedes from galaxy 2 at V greater than C. And that's fine, that's completely allowed, and it's not a problem. What it also means, though, given that there is no preferred location in the universe, the galaxy here has a horizon which extends over here, and the galaxy here has a horizon which extends over here that we cannot see. We don't think they're seeing an edge of the universe here. We don't think they're saying, oh, we can see more universe in one direction than the other. And so what that actually means is that almost certainly, although we can't observationally test it, there is lots of universe that we can't see. So that is beyond the visible universe. And so that's sort of implication for relativity in terms of special relativity and cosmology. And then let's look a little bit about an implication from general relativity, and that comes from the idea of the equivalence principle. And a lot of you will have heard of the equivalence principle. It's an idea that's very fundamental to general relativity. It's a thing that leads to curvature, as we'll see in a minute. You can write it down actually in lots of different ways, but an important way of writing it is the following. If I write a gravitational force, and I write therefore that F is just minus G m1 m2 over r squared, and I write, that's a gravitational force. And then I write Newton's second law, F equals ma. Then I have two kinds of mass here. Here, I have a gravitational mass. And here, I have an inertial mass. In other words, the mass that appears in Newton's second law is the resistance, or a measure of the resistance that a body has to a force, to an acceleration. So the inertial mass and the gravitational mass appear in these two equations. And although, of course, Newton has always assumed this, one statement of the equivalence principle is to say inertial mass is equivalent to gravitational mass. And that comes with a rather simple thought experiment, which if that is true, then you can't distinguish locally, i.e. in a small laboratory, between uniform acceleration or a gravitational field. And again, to put that in context, that means I could be, imagine I'm, in some free-floating laboratory. And this laboratory, I haven't got any windows, I can't just look out to see where I am. And so it could be doing one or two things, right? Not necessarily free-floating. I could have something which is accelerating with A equals G, for example. Or alternatively, I could have my laboratory, in fact, sitting on a surface with a gravitational field coming down. And the equivalence principle, therefore, because the inertial mass is equivalent to the gravitational mass, tells me that these two things are directly equivalent. That means I can't do any experiment if this is frame A and this is frame B. No experiment performed in laboratory A can distinguish from laboratory B. So I can't do an experiment in one that varies from the other. Now, if I shine a light across here, of course this is an accelerating frame, so it's not just moving at a constant velocity, it's accelerating. So in the time the light takes to cross it, it's actually sped up, you know, imperceptibly. So if I fire a light, the light won't go straight across, it will hit at some lower point because of the fact that since this light has moved, and of course, you know, that means it's moving directly across in that frame, has to travel at the speed of light, of course, a consequence of special relativity. This light is going to hit lower on this side of the laboratory than it is emitted on this side. So therefore, one experiment I can do inside this laboratory is I can fire light and I can measure where it impacts on the other wall. I can see that it impacts lower than it's sent, and therefore that tells me that I'm in an accelerating frame. But it can't tell me that I'm in an accelerating frame because in principle, if I do the same experiment over here, I should see the same thing. Now, in principle, photons are massless, they're not affected by gravity. And so I should, if I just, on the surface of the Earth, if I fire a light across the room, it should just go and hit exactly at the same level. And so what these two things tell me is that we know that A has to happen. If B is going to look the same as A, therefore, if A and B are indistinguishable, then the light in B must be curved by gravity. And so that leads you to the idea that mass causes curvature. And although we're not going to worry about it in the course of this course because it's not something, you know, we're not going to do a relativistic cosmology course, we're going to do a Newtonian cosmology course, you can actually think in a very different way, therefore, about how a general relativistic example looks different from a non-relativistic example. And so you've got Newton, and it says mass tells gravity how to exert a force, and force tells mass how to accelerate. And then you have Einstein, and in our Einsteinian view, we have mass, and formally it's mass energy because you have E equals mc squared, tells space-time how to curve. And curved space-time tells mass energy, i.e. things like the photon, how to move. And so when I use words like curved up here, what I really mean is not that the light is curved, it's actually following the straightest path it can, the shortest path it can, through a curved space-time. But what that in turn means is that you have to acknowledge the possibility that since the universe has mass, it may have curvature. very well. And what does that mean, and how would you even think about what curvature is? Well, a simple way to think about it is if I draw a triangle on a bit of paper in a Euclidean space, i.e. x, y and z run at right angles to each other, a flat Euclidean space, x, y and z are at right angles, and if I draw a triangle like this, I've not done that very well, I have 3 internal angles on my triangle, and again, for some reason I'm not doing very well here, and I'll call them alpha, beta and gamma. If I have alpha plus beta plus gamma in a flat Euclidean surface, well, we know what they add up to. They add up to 180 degrees. On the other hand, if I have a surface of what we call positive curvature, and we'll also think about that as spherical, then what I have is I have something different. So if I draw here, and if you look in the PDF, there'll be a slightly better diagram of this. Imagine that this now is a sphere. And of course, a sphere has these great circles. So imagine this is the Earth, and you've got the equator, and then you can have another line, which is another great circle here, and another line, which is another great circle here. And so my triangle here, alpha, beta, gamma, from the equator I can go straight up to the pole. I can then turn at right angles and go straight down to the equator again, or I can turn at right angles and come back to where I started from. So in other words, on a spherical surface, a surface like the surface of the Earth, a triangle can have internal angles, 3 straight lines, just go straight, 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 which add up to substantially more than 180 degrees. So on a positive circle, positive curvature, you have alpha plus beta plus gamma greater than 180 degrees. And then you can have the alternative, and this is slightly harder to visualize. You can have a region which has a negative curvature, and we'll sometimes call that hyperbolic. And you can think about hyperbolic, it's like the inside of a donut or something like that. Think about drawing a triangle on the inside of a donut, and then your triangle will look something like this. And alpha plus beta plus gamma is less than 180 degrees. And so the punchline here is that because the universe contains mass energy, so matter and photons, it might have a curvature, and that curvature depends on its mass energy, just how much mass energy there is. It also tells you that if you're going to be worrying about how the universe is going to evolve, then thinking strongly about energy is a good place to start. And so that's what we can now do, bearing these concepts in mind, is to start building an actual model or a set of equations that will model the universe.